So let's go ahead and talk about Chapter 3. In Chapter 3, what we're doing is we're looking at something called a derivative. And the whole chapter is going to be on what is a derivative and how do I use it. And then we're going to have Chapter 4, which is kind of going to double down and say, all right, what is a derivative useful for? What sort of applications can I do with this? So if we remember back to our introduction of calculus, we said that there were sort of two main motivating problems. One of them was how to find a tangent line to a graph, which can translate into lots of other things like how to find instantaneous velocity. And we're going to see lots of things that are sort of equivalent to solving this problem, but that's the way that we're going to look at it initially. Okay, so so Chapter 3 is all about the derivative. Okay. So let's start the chapter by explaining what this is. And this is going to go, I think, a little bit better than limits, where limits were a little bit confusing. And we said, all right, we're going to get a rough idea, and then we'll define it precisely at the end. That's not going to be true here. We're going to define the derivative precisely from the beginning. But I do want to get an intuitive sense for what a derivative is first. Okay, so our section 3.1 is going to be defining the derivative. So if we remember back to the tangent line problem, okay, suppose I have a graph of some function. I want it to have some curviness to it. Okay, and let's suppose I pick a value. We'll say that this is A, and I want to find the tangent line to the graph at A. Okay, the way that we looked at this before was we said, okay, pick another value on the graph and connect them with a line. Okay, and as I pick points that are closer and closer to A, my lines will converge on a graph of a line that looks closer and closer to the tangent line. And so we have that sort of successive approximation, and by getting infinitely close using a limit, we can get the tangent line. Okay, that's the rough idea of what we want to outline here. Okay, so we're going to start by talking about tangent lines and looking at slopes of tangent lines so that it starts to make sense for where our definition of a derivative comes from. Right. So let's start by looking at the slope of a secant line. Now, a secant line is not like a new strange thing. What I want to do is look at this same graph that we just drew. Try to draw the same thing again. The secant line is just when we pick a value, we pick 2 points and we connect them with a line. Okay, and maybe instead of calling it, so here we have an A value, and I want to label the second one. I didn't back here, and we'll do that in the future, but let's call the second one X. Okay, then the Y value is f of A for the first point and f of X for the second. Okay, and I know that slope is just change in Y over change in X. So the slope of the secant line and we can write M for slope, and I'll just write a subscript SEC for the secant line, is f of X minus f of A over X minus A. Okay. There's another way to formulate this, though. if I think about this idea that I have over here on the left, where I'm thinking about that x value moving, getting closer and closer to a, I'm not thinking about picking x values at random. I'm picking x values that are a certain distance away from a. So maybe instead of talk about a separate x value, we'll talk about a, and we'll talk about moving over from a by a little amount. Okay, so we can think of x as a point, or yeah, we'll just call it a point for now, a small distance away from a. Okay, and what I'm going to do is I'm just going to call that small distance h. Right. So then if I redraw the same graph, and I'm going to try to draw the same function, but it doesn't really matter. Like, so up, down. Okay, we have our a value. And what I'm going to do is I'm going to think of this second point as being a plus h. So this distance between is just h. Okay. So x equals a plus h. Oops. Okay. And then f of x would equal f of a plus h. All right. So let's see what that does to our little formula that we just created, right, for the secant line. We have f of a minus f of x. I'm sorry, we wrote this the other way. F of x minus f of a. All over x minus a. So I'm going to replace my x with an a plus h. Okay. And down here, the x that's by itself, I can replace with an a plus h. But a minus a can cancel, so I just have f of a plus h minus f of a all over h. Okay. It looks like a different formula, but it's the exact same thing. I've just relabeled things so that I'm focusing on that distance between the 2 points. All right. So let's have a definition. So let f be defined we'll just say it's a function. It's defined on some interval containing a, right? But we'll this thing that we're working with, this slope of a secant line, I'm going to label as something. So f of x minus f of a over x minus a is called a difference quotient. Okay, and we might refer back to that a few times. Okay. Also, f of x minus f of a over x minus a is the same as f of a plus h minus f of a all over h. Okay, where h is just equal to well, I should say x is equal to a plus h, or h is equal to x minus a, right? Kind of the same thing. Okay. All right. Now, this gives us a way to look at the slope of a secant line. And the idea that we were discussing earlier was, as that second point gets closer and closer to A, the slope of the secant line approaches the slope of the tangent line. Okay. So what we're going to do is we're going to define that to be the slope of the tangent line, because we don't really have a definition for that. Okay, so we're just going to say that's what it looks like it should be, so we'll just say that's what it is. All right. So the slope of the tangent line to f of x at x equals a is the line, or sorry, is we can write this as m tangent. And what we're going to do is we're going to take that same difference quotient we just had, f of x minus f of a over x minus a, and we're just going to throw a limit up the front. And we're going to say, all right, let that x get closer and closer to a. Provided this limit exists. Okay. And so there's a couple of things that I want to note here. Note that this same slope, we just said that the difference quotient is the same if I define things with that h instead of the x's. Okay, so I can write this as f of a plus h minus f of a all over h. We have to be careful though about what's going on with the limit. What happens as x gets closer and closer to a? Well, if h is defined to be x minus a, as x gets closer and closer to a, this difference is going to get closer and closer to 0. Okay, so this is like a limit as h goes to 0. Okay. Also, the tangent line to f at x equals a is the line with this slope that passes through the point a comma f of a. All right, so that's the definition and buildup. Let's go ahead and look at an example and see if we can't, make sure that we are following all of this theory here. Okay, so here's our example. Find the tangent line to f of x equals x squared minus 3x plus 1 at a equals 2. Okay. All right. What I'm going to do is exactly just follow this definition. And I'm going to show you the difference between these two formulations we have. So I'm going to start my first example with using our our initial formulation where we have the x's and the a's. And I'll show you why we don't really want to keep using that going forward. Okay, so what we do is we say, all right, the slope of the tangent line is the limit as x approaches a, which is 2. Well, here, let me write it out. I'll write out the f of x minus f of a over x minus a. And then we'll say, okay, my a value is 2. And f of x is x squared minus 3x plus 1. So that's the f of x. F of a is 2 squared minus 3 times 2 plus 1. Okay. So let's just figure out what we have going on here. I'm going to simplify this, right? 2 squared is 4, minus 6 is negative 2, plus 1 is negative 1. Wait. 4 minus 6 is negative 2, plus 1, negative 1. Yeah. So I have x squared minus 3x plus 1 minus negative 1 in the numerator, and x minus 2 in the denominator. Okay. I'm going to treat this like a regular limit. I just wanted to simplify things down first because there was so much stuff to write. So I'll do one more step. 1 minus a negative 1 is 1 plus 1, or 2. So I'm going to write this as the limit as x approaches 2 of x squared minus 3x plus 2 over x minus 2. And what we did in the last chapter when we were working with limits, my suggestion was to always try direct substitution and see what happens. So if I try direct substitution, I get 2 squared minus 3 times 2 plus 2 in the numerator, 2 minus 2 in the denominator. And the numerator, 2 squared minus 3 times 2, right, that's 4, minus 6 plus 2 gives me 0. Okay, so that tells me that I can't do direct substitution, but it also tells me that x minus 2 will be a factor in the numerator. Okay, so then x minus 1 must be the other factor, because to multiply and get x squared, I have to take x times x. To multiply and get a positive 2, I need a negative 2 and a negative 1. Okay, so then my x minus 2's cancel. So I'm just left with the limit as x approaches 2 of x minus 1. And now when I do direct substitution, I get 1. So that's the slope of our tangent line. Okay, now we need to find the equation of a line. Okay. So let me just remind you. There's more than one way to find an equation of a line, but what we're going to often see in this chapter is a line where we know a point and we know a slope. So we're going to use the point slope formula for the line. Y minus y1 equals m times x minus x1. Maybe just to give you a quick background of where this comes from in case you've never seen it. I know that slope is y2 minus y1 over x2 minus x1, right? That's my slope formula, change in y over change in x. If I pick one of my points, instead of to be a fixed point, call it a flexible point, x comma y, I could write this as slope is y minus y1 over x minus x1, and then just multiply both sides by that denominator. M times x minus x1 is y minus y1. Okay, that's where this equation for a line comes from. It's just the point slope formula written without a fraction. Okay, so if I use that back here, well, I need to figure out my point first. I know that my x value is 2, right, because we have this a equals 2. Right, so f of a is 2 squared minus 3 times 2 plus 1. Which I think we said was negative 1. Okay, So we have a slope of 1 and a point 2 comma negative 1. And so when I use my point slope equation, think of this as x1 comma y1. And when I plug in, I'm going to get y minus negative 1 equals 1 times x minus 2. So y plus 1 equals x minus 2. When I subtract 1 from both sides, I get y equals x minus 3. So there's my equation of a tangent line. All right, I want to do a second example, or maybe what I'll do is I'm going to redo this problem, but I'm going to show you how to, I'm going to use the other formulation that we have for slope of the tangent line. Okay. What if we use that the slope of the tangent line is this limit with the h's instead? Okay, so remember that we were using an a value of 2, and my function was x squared minus 3x plus 1. All right, yeah. Okay, so before I write this difference quotient down, let me just put the pieces together, right? So f of a is f of 2, which we computed a second ago, negative 1. F of a plus h is f of 2 plus h. So I'm just replacing in my formula here my x with 2 plus h. So in my output formula, I replace the x with a 2 plus h. Okay, so let's work that out a little bit. The 2 plus h squared I have to FOIL out. So that's going to be 2 squared plus 2h plus another 2h plus h squared. And then over here I distribute the negative 3. Okay. And now grouping like terms, I have h squared. I have 4h minus 3h gives me 1h. And then 2 squared is 4 minus 6 gives me a negative 2. And then plus 1 gives me a negative 1. Okay, so the slope of the tangent line is going to be the limit as h goes to 0 of f of a plus h minus f of a all over h. We said that f of a plus h, I simplified that already. Let me rewrite my limit real quick. That's h squared plus h minus 1. F of a we said is just negative 1. Okay, negative 1 minus negative 1 gives me 0. So this is the limit as h goes to 0 of h squared plus h over h. And I need to cancel this h in the denominator in order to do anything with this limit. So I'm going to factor an h out of the numerator. Okay, so now we can cancel this h. And now I can use direct substitution to solve this. H is approaching 0, so I replace my h with a 0. Okay, and we get the same slope that we did before. What I want to do is point out the difference. When we look at f of x minus f of a, we're going to end up with something that you have to factor, which is okay, and in the case of a quadratic, that's actually pretty easy. But we're always going to end up with something that we're going to have to factor and cancel with. When I do this other formulation, I didn't really have to factor. The only thing I'm going to factor out is an h to cancel an h, and that's always just going to either be there or it's not. There's no work involved there. I do have to do extra work with multiplying stuff out. So the difference is that in this formulation, I have to factor, and in this formulation, I have to multiply. And if I were just to pick up a problem off the shelf, typically multiplying stuff out is easier than factoring. Okay, in certain special cases like this one, it's a simple problem, so then the factoring is very easy, and so it's faster. But for most problems that are complicated, factoring gets much harder. Multiplying doesn't really get any harder, right? If you add layers of complexity, it takes a little bit more time, but it doesn't get more difficult. Factoring gets a lot more difficult as you make things more complicated. Okay, let's look at another example. Let's suppose I have a fraction. So find the tangent line. Okay, to f of x equals 1 over x at a equals 3. Okay, so I'm going to start off by finding my point, right? So I have an input value of 3. So I need an output value. F of a is 1/3, right? So we have a point 3 comma 1/3. So now we need a slope. The slope of the tangent line. I'm just going to use one formulation here. I'm just going to use the limit as h goes to 0. So this is f of a plus h minus f of a all over h. Now, with all of these problems, I like to compute f of a plus h separately because there's a bunch of work there and I don't want to have to rewrite the limit and all this other stuff, this big fraction. So I'm going to compute that off to the side. I'm going to say, okay, f of a plus h is f of 3 plus h, which is 1 over 3 plus h. And here there's no simplifying to do, so I'm just done. Right? Okay. So we end up with the limit as h approaches 0 of 1 over 3 plus h minus 1 over 3, and all of that is divided by h. Okay, and we've seen limits like this. In chapter 2, we looked at stuff that looked exactly like this, right? And that was on purpose. So we know our strategy, right? We're going to get common denominators. So I'm going to multiply my fraction on the right by 3 plus, oh, that's too light to see. So I'm going to multiply this fraction on the right by 3 plus h on top and bottom, and the fraction on the left by 3 on top and bottom, so that I have a common denominator. Okay, so we still have this equal to the limit as h goes to 0. The fraction on the left is going to be 3 over 3 times 3 plus h. Now, remember what I've said before, when I'm subtracting a fraction, I don't like to do that. I like to change it to adding a negative so that I don't lose my negative. Okay, and I do that right away. So I'm going to write plus, and then I'm going to have negative 1 times 3 plus h all over 3 times 3 plus h. Okay. Now, I also don't like having multiple layers of fractions, so I'm going to rewrite this right away. Instead of dividing by h, I can write this whole business as being multiplied by 1 over h. Okay. And that keeps the different layers to a minimum, and so I'm less likely to lose a term or make a mistake. Okay, now I have the same denominator, so I can add these two together. Okay, so I have 3 on the left. On the right, I'm going to distribute it, so I have minus 3 minus h. And everything else stays the same. Just like we talked about in chapter 2, when we get this common denominator, we don't want to multiply it out because that's not really going to be helpful. Okay. In this case, it wouldn't hurt us, but it's not really that useful. All right, now I simplify. 3 minus 3 adds to 0, and my whole goal is to cancel this h in the denominator. So I'm hoping to be able to factor an h out. Well, what I'm left with is a negative h. Okay, so when I factor an h out, right, if I rewrite this as negative 1 times h, then I can cancel my h's, and I'm left with a negative 1 in the numerator. So now we do direct substitution. 3 plus 0 is 3. 3 times 3 is 9. So I have negative 1/9. Okay. So then if I want to create the equation of the tangent line, y minus y1 equals m times x minus x1. We go back and remember our point was 3 comma 1/3. So y minus 1/3. Our slope is negative 1/9. We have x minus 3. Okay, and then from here we just do a little bit of algebra to simplify. I'm going to distribute the negative 1/9. So I have negative 1/9 x. Negative 1/9 times a negative 3 is going to be a positive, and 1/9 times 3 is 1/3. Okay, now I add 1/3 to both sides. So I have y equals negative 1/9 x plus 2/3. Get the y equals. Okay, so that's our equation of the tangent line. What I'd like to show you is what this looks like on a graph. So the function we were looking at is 1 over x. So if I graph y equals 1 over x, and that's in blue, and then I'm going to graph the equation of my tangent line here in red, y equals negative 1/9 x plus 2/3. Okay, and we can see in blue there's our graph, and in red there's our tangent line. Let's bring our zoom window in a little bit. We're looking at this at a equals 3. We'll just have x values that go from 2 to 4. That window a little bit smaller. Okay. And you can see, my red tangent line just kind of hits the graph and goes through, so that's kind of a nice tangent line there. Okay. So yeah, that's all we're really doing. We're saying, all right, here's my graph. Find that line that just touches that graph and then moves on. Okay. So now let's talk about what are other things that have the same formula as slope. Okay. When we started this investigation, we didn't actually start with slopes. We started a conversation talking about Newton and how he's probably talking about things like velocities and stuff, right? And we talked about instantaneous velocity. Okay. So I'm just going to write down a formula for speed or velocity. We will very shortly in the course talk about the difference between speed and velocity. The distinction is that velocity has a direction to it and speed doesn't. So if I say I'm driving my car and I'm going 70 miles an hour, that's a speed. If I say I'm going 70 miles an hour north, that's a velocity. So if I look at speed, right, and we'll just kind of conflate the two a little bit right now, and we'll make this distinction a little bit more clear later. But if I'm talking about speed, or if I'm talking about the velocity or magnitude of velocity, we just want the change in distance over change in time, right? So we could write this as if s of t is position at time t, okay, then my speed is going to be, s of t2 minus s of t1 over t2 minus t1, okay? So my instantaneous speed, or we're going to call this instantaneous velocity. And the reason that we can get away with it is if I think about things moving on a line, then my directions can just be positive and negative, and I don't have to worry about directions in a plane or in space or anything like that. So if I said instantaneous velocity at time t equals a, okay, then that would be the limit as h goes to 0 of s of a plus h minus s of a all over h, okay? And so then, you can see this is exactly the same as slope was, right? And so mathematically, everything that we do with slope could just is easily applied to velocities, right? So when we do these, some of these mathematical investigations, right, we're not really solving like this one obscure math problem. What we're doing is we're kind of solving a general idea that can be applied to lots of different things. Now, I didn't really give you lots of different things. I said, oh, this is velocity. But we could have lots of, if I just change what my function means, then I'm going to have something else. And really, all I'm doing is looking at, a change in my function. And if my variable is time, it's like over time. So I could just think about like a rate of change. Okay. So for any function f of t, okay, we have an instantaneous rate of change. So the instantaneous rate of change of f at time t equals a is the limit as h goes to 0 of f of a plus h minus f of a all over h. Okay, so this is instantaneous rate of change, and here's our formula. Okay. As opposed to the average rate of change, from time t1 to time t2 is f of t2 minus f of t1 all over t2 minus t1 with no limit. Okay, so to give you a little bit of context, or bring it back to the context that we've talked about before, instantaneous rate of change is like slope of the tangent line. Average rate of change is like slope of that secant line that connects 2 points on the graph. Okay. And this can be for anything, right? So if we were talking about, if my function is temperature, then we could talk about, rate of change of temperature over time. If my function is talking about the, energy in, some sort of chemical compound, we could talk about the rate of reaction. We could have the average rate of reaction or the instantaneous rate of reaction. In economics, we could talk about, profit. And when you talk about like things like instantaneous cost and profit and revenue, we have a special name for that. We call that like the marginal profit, okay, or the marginal cost. And so that gives us the stuff. Now, it's helpful to have a way to refer to that, right? So back at the beginning, when we were talking about tangent lines, okay, let's see, when we defined it, we said, okay, this is a difference quotient. And then we said, all right, when we throw that limit out front, we get the slope of the tangent line, right? So we had this concept of the slope of the tangent line. And we said, okay, that's this difference quotient with a limit out front. But if I change the context, then I'm not talking about slopes of tangent lines anymore, but I might want to refer to the same idea, right? So we want to give a name to this thing that we're talking about independent of its context, so we can always just refer back to it and have the same formula, right? So that's where we're going to get a label for it, and we're going to call this the derivative, okay? Okay, so definition, the derivative of f of x at x equals a which is written f prime of a is f prime of a is the limit as h goes to 0 of f of a plus h minus f of a all over h. Okay. So this is what a derivative is. Okay. At a single point. And in this section, that's what we're going to look at. We're going to say, all right, if I have specific points, let's look at derivative at that one specific point.